In number 44, we have four objects: a hoop or a ring, a solid cylinder or disc, a solid sphere, and a thin spherical shell. All of them have the same mass and the same radius. Part A asks us to find the moment of inertia or rotational inertia for each object as it rotates around the axes. Take a quick look at it. For the hoop, just mr squared. Plugging in numbers gives us that. The cylinder, 1/2 mr squared. Plugging in our numbers gives us that. The sphere, 2/5 mr squared, gives us that. And the shell, 2/3 mr squared, gives us that. And I've color coded these to sort of match what you see over there. You'll notice that the loop, or the hoop, has the greatest rotational inertia. Therefore, it's the most difficult to get rolling, and it's lagging behind all the rest. Whereas the sphere has the least amount of rotational inertia, and it's the easiest one to start rotating, and it easily wins the race, even though they all have the same mass and the same radius. And this goes down to part B. Suppose each object is rolled down the ramp. Rank the translational speed of each object from highest to lowest. So this is asking, what's the final velocity at the bottom of the ramp? And you can visually see it, and we've already talked about it. The sphere ends up with the largest speed at the bottom. It's the easiest one to get rotating. And the hoop, the most difficult, ends up with the smallest speed at the bottom. It doesn't get much velocity at all. Part C now, though, rank the object's rotational kinetic energies from highest to lowest. Now, for this, you got to do a little bit of thinking. We know the initial energy they all start out with is gravitational potential energy. There's no work done by friction as they go down, or at least we're not told any. And the final kinetic energy at the bottom is going to be both kinetic energy and rotational kinetic energy. And now here's where the logic comes in. All of them have the exact same mass. And again, just a quick reminder, kinetic energy is equal to 1/2 mv squared. They all have the same mass, but they have different velocities by the time they get to the bottom. So which one has the greatest kinetic energy? Well, since the sphere had the greatest velocity, it's also going to end up with the greatest kinetic energy. Likewise, the hoop, which had the smallest velocity at the bottom, is going to have the smallest kinetic energy. Again, remember, they all have the same mass. And likewise with the cylinder and shell. And then here's where we got to do a little bit of thinking. So the sum of the kinetic and rotational kinetic energy at the bottom has to be the same as the mgh it starts out with. Please remember that they all start out with the same amount of gravitational potential energy, mgh. But now, if the sphere has the most regular kinetic energy, what's going to be true about its rotational kinetic energy? Well, it's going to be the least. And so this ends up being exactly reversed. The sum of the kinetic and rotational kinetic energy has to be the same for all these, but since the sphere has the most regular kinetic energy, it's going to have the least of the rotational kinetic energy. And the hoop, which has the least regular kinetic energy, is going to have the most rotational kinetic energy. This is your answer then to the other part. Enjoy!